Hello and welcome to another episode of High or Log Maths, which is all about how mathematics can improve our mental and intellectual abilities. This is not a technical show, which means we won't present mathematics formulas or abstract stuff. Rather, we talk about challenges, problems, solutions, research, and discoveries in the world of mathematics and its applications. My name is Linda. I'm the host of the show. I'm applied mathematician. I completed a PhD in it. I'm also a maths educator and the founder of Bungee Pie, which helps children learn mathematics using storytelling, animations, and real life applications. It also helps maths teachers and schools develop numeracy, problem solving skills, and critical thinking of their students. Today I'm honored to have Dr. John Adam, who is super duper well experienced and knowledgeable applied mathematicians. Believe me, he is impressive to talk about patterns in nature. So hanging there, he will show you so many pretty cool photos and tell you how you can use maths to find patterns in them. Let me give you a brief introduction about him first. Dr. John Adam has been Professor of Mathematics at Old Dominion University, located in the coastal city of Norfolk, Virginia, United States of America since 1984. His PhD from the University of London was in theoretical astrophysics. As an undergraduate, he was exposed to a concentrated diet of Monty Python's Flying Circus, and he has never fully recovered from it, even at his advanced age. His first introduction to the United States of America was through the humor of the Far Side cartoons by Gary Lawson. He has broad interest in mathematical modeling and applied mathematics. He is a frequent contributor to Earth Science Picture Day. In 2007, he was winner of an Outstanding Faculty Award for the state of Virginia. In 2012, he was a recipient of a Cole Allendefier Award from Mathematical Associations of America. He has published approximately 120 scientific papers and has given over 180 presentations to professionals and university groups. He has published several books, all published by Princeton University Press, and he will talk about it during his presentation later. Dr. Adam also enjoys writing resource articles on applied mathematics for teachers. Isn't that impressive, really? A long-time contributor to the world of mathematics and its applications. Welcome to my show again. I'm quite honored to have you. When I was going through all your background and what you have been doing in the space of mathematics education, maths modeling, applied mathematics, and all of the crazy things. I was so impressed. And I was thinking, oh my God, I really appreciate the fact that we have this social media, LinkedIn, and this pandemic to really make us closer to each other and find quite amazing, impressive people. And I would like to thank you for accepting to be part of this show and give us a bit of insight of some of the works that you have been done. And I'd love to invite you back again to talk about more interesting things because I'm pretty much sure you have a lot to say. So let's start with the first question, which is about well, you need to share a little bit about yourself. So, what did you want it to be growing up?
Well, that's a great question because at the age of around 13, I came across a book called The Observer's Book of Astronomy by Patrick Moore, one of a series of observer's books on different topics in nature, butterflies and flowers and so on. But I devoured this book, so to speak. I really got interested in it and so excited. I wanted to be an astronomer.
Oh, wow.
Okay. And I grew up. My parents it was a very working class home. We never owned a home of our own. My parents didn't have a lot of money, but they were so excited that I wanted to do this, that they actually bought a small telescope for me at great expense.
Wow.
£25 then, which was quite a lot of money, a beautiful brass telescope, and you'll see a picture of it later.
Right.
And when I was about 14, the algebra teacher at the school I was attending, Henley-on-Thames Grammar School, was going around the class asking us what we wanted to be. And I stuck my hand up and said, "Oh, an astronomer, sir." And a very
Right.
worried look came over his face. And he said, "Adam," because they referred to us by our last names,
Yeah.
"Adam, even observational astronomers need to know a lot of mathematics.
Wow.
You are bottom of the class in algebra."
Right.
Now, he was being realistic. I had the choice, I suppose, at that time of just getting discouraged or just working my tush off
Right.
to just keep going, and I did that.
Right.
I would love to have had the opportunity to go back and after I got a PhD in theoretical astrophysics,
Right.
but I never did see him again. But anyway, so that's really propelled me. I just kept working and working and working at it. I wasn't the best in the class, obviously being bottom in algebra, but I pulled myself up in that sense.
Wow. It's impressive. It's just amazing, like how teachers can shape our life or future or direction. It's
Yes.
so impressive, and the more I get to know quite impressive people, very successful people, the more I realize how teachers really, at some point in their life, they had kind of a role model, a teacher who actually contributed in terms of shaping their ideas, shaping their directions, like pointing out something to them. And it's so interesting how teachers are playing a big role in our life.
He was a sort of anti-role model in that sense. And I will share something else. Because I was determined to be an astronomer, which
Yeah.
I never eventually became, but because I wanted to do that, I worked really, really hard. I spent all my time in mathematics and physics and studying.
Right.
It took me sometimes whole weekends to complete my geometry homework that my
Mm.
brighter friends could do in half an hour. And even then, I only got 8 out of 10 or something like that.
Wow.
And when I graduated from high school, one of the report cards I had from another mathematics teacher
Yeah.
was a sort of backhander, really. It said, "Adam, by dint of sheer hard work, is sometimes able to outperform his far brighter peers."
Wow.
But because I had to work at it, once I grasped something and understood it, I knew I had it. It was mine, and I could share it.
Right.
Whereas my brighter friends were sometimes bored with it because it was so obvious.
Yeah. Yeah. I get it. And I see a lot of value in it. As soon as this is yours, and you put a lot of hard work in it, I think you do appreciate it more. And this is something that I do believe in, and I do appreciate. All right, coolly. So, what about your career path? Tell me about that. I
I,
know it has been quite an interesting one, but
yes, I would say somewhere between meandering and fractal-like.
hmm,
In so much as I've done a lot of different things, and basically, when they got too hard for me, I moved on to something else.
right,
So it's been limited by the fact I don't do much computing. I never really got into that side of things, so it was
right,
mostly analytic stuff. But from a physics bachelor's degree to a theoretical astrophysics PhD to magnetohydrodynamics, stability theory, differential equations, mathematical modeling in biology, tumor growth models, wound healing models, and more recently meteorological optics. And now, most latest of all, is basically working on resources in applied mathematics for middle and high school teachers.
wow, wow, that's great. That's a lot of work. I
Well,
really do. I would dedicate it
sorry
to
to
that.
interrupt. I'm a jack. They have this expression in the UK. In Britain, you may be familiar with it as an Aussie. I'm a jack of all trades and master of none.
Oh, my, that's great. That's really good. Right. I would just from what the look of what you've done so far. I know you're so passionate about this stuff you've been talking about, but I would like to I actually ask this question: is there anything else you're passionate about? It's just all the maths maths in life, or
Well,
maths in life is just your things?
um, I feel like I can only do one thing quite well, and this is it. But I would say that uh, what's underlined um, my my teaching in the last, I suppose, well, since I had open heart surgery, actually, and a heart attack in
Oh
1996,
no.
since that time, I've been fascinated by what I can put succinctly as the beauty of nature as revealed by mathematics, and the beauty of mathematics as revealed in nature.
Right. Yeah.
But are you talking about outside of my chosen field? What makes me passionate?
Whatever.
Well, just nature. But my wife and I will have gone to a lot of national parks in the US, and they are beautiful. Somebody said it was Ken Burns who said it was uh, America's best idea. There's such a lot of beauty there, and of course abroad. I'd love to
Yeah.
visit Australia,
Right.
uh, but so that's really what drives me. Beauty of nature. It doesn't have to be mathematical, but
Right.
just awe-inspiring images and
Yeah.
breathtaking
Yeah.
uh, scenes. And I do a lot of nature photography. I
Right.
point my camera and I press a button, and that's basically it. And sometimes it comes out well.
I love it. I love it. I do photography. I don't know if I told you or not, but I do
No.
photography, the professional one, because I really like photography. And I'm very a fan of like going out in nature. I love nature, and nature photography is my thing. I think it's really, really amazing. And the fact that you have that maths mindset, and you can look at the shape like a flower, or the bird, or the tree, or the leaves, or whatever, and you can see the pattern, you can see all the curves, or you can, in your mind, you can like match it with something that you know already. And I think it's fairly cool. And it's great that you want to talk about it today, share us with the pretty photos, and talk about patterns, and things like that.
Some people think that mathematics is mental abuse to humans, and this is something that I
Like that.
want to sort of get over. Uh, so, in the patterns that I'm going to show you, there's a lot of implicit mathematics and physics in their descriptions and explanations. But I want to issue a warning that I give to my students, and I would give to everybody. Don't get on your cell phone when you're outside. There's so much to see above us and around us. Certainly don't do it when you're driving or operating heavy machinery, but just keep your eyes open. You never know what you may see.
Oh wow, this is so cool. I like it.
An interesting juxtaposition. Also, here's a flying fish with a one-way ticket. And just remember that because you're going forward doesn't always mean you're going to a better place.
Definitely true.
So I want to talk a little bit about the philosophy and history of theoretical optics, because essentially we see things because of light reflected off them. And so you might find this interesting. Now, I'm going to share something called coaster philosophy.
Right.
After my mother died in 2007,
Yeah.
those of us who were celebrating her life were in a British pub and having a beer or five to honor her. And there were some coasters, like little squares about 3 inches on a side, with on which you put your beer.
Right.
In America, they don't know what beer mats are, so that's why I've used the coaster. But on one side of this one I had was a lovely quote from the French composer Claude Debussy.
Mm.
Music is the arithmetic of sounds, as optics is the geometry of light.
Oh wow.
That's very profound. It
Yeah.
really is. And I love it. And on the other side, you just pick a chord, go twang, and you've got music by Sid Vicious, who was the late great bass guitarist of a British group called the Sex Pistols.
Mm.
And then further down it said, in fact, I don't have it, but I thought I did. It said, not everything in black and white makes sense. Guinness. And so I'm surprised. I should have had that picture there. Anyway, one of these is Claude Debussy, and the other is Sid Vicious. And I'll leave it to your viewers to decide who is who. Uh, okay, there are two other very important gentlemen I want to introduce. This is not, in fact, Inigo Montoya from The Princess Bride. Hello, my name is Inigo Montoya. You killed my father. Prepare to die. Of course, it's Rene Descartes,
Yeah.
much beloved by or hated by mathematics students because of various things, but combining geometry and algebra. And of course, we have the coordinate geometric system, Cartesian geometry. And he made a great contribution to the kind of mathematics that essentially our second gentleman used a lot. Who is that second gentleman? No, that's a mistake. This is an improvement, but we're getting there. It is Isaac Newton. Here's a collage, and I don't know whether you can see here on the top left, he's having a very bad hair day. But as a younger man on the top right, this is taken from this image on the bottom right, where he's performing his classic experiment of allowing a shaft of light to come through a hole in a blind and passing through a prism to separate the constituent colors of white light. Now, on the left here, bottom left, we have the famous painting by Blake. And we have been so inspired in our mathematics department by this painting that we make sure that anybody who applies for a master's or PhD program in mathematics gets to sit naked on a sharp, pointy rock and prove theorems. And you won't believe how much that separates the sheep from the goats, those who are serious from those who are not. Of course, I'm joking, in case anybody does want to apply for a program here. So this is what was going on, of course, the famous visible spectrum. Yeah. And here is a picture of Isaac Newton. It looks like he's trying to get a signal on his cell phone, and finally he's called his auntie in Australia, got through to her, and the ladies there are very pleased. Anyway, being black and white, you see that then I can make that kind of joke. All right. So, nature's patterns. No graduate students or other animals were harmed during the preparation of these slides. Okay, so here's a picture of the visible solar spectrum. And of course, we learn early on, we're told that there's only 7 colors: red, orange, yellow, green, blue, indigo, violet. But, nobody's ever seen indigo. And in fact, there's an infinite number of them. They're not well demarked. I'm going to be asking questions without answering them totally here, because I want people to think about these. Right. And we can always come back and go into more mathematical detail another time if you decide that you want to talk to me again. So why are rainbows circular arcs? Here's a nice picture. You can find a lot of these on the web. You can see here a double rainbow, of course. The shadow of the photographers here at the center of what will turn out to be a cone. We're looking on the surface of a cone. This is a darker area in between, and there's our secondary bow with the colors reversed. It's fainter because there's an additional reflection. And here are things called supernumerary bows, which are very interesting and actually allowed the wave nature of light to gain ascendancy over the corpuscular theory of light. It was something that Newton could not explain. Wow. Nor Descartes, in fact. So I've just got a selection of pictures here. Depending on the size of the raindrops, you'll get a variety of intensities and distribution of colors. And this is another lovely one. You can just about, or I can see a faint secondary around here. Yeah. And then these are actually only one of these is a real rainbow taken outside my house. The others are spray bows. When my wife wanted me to water the plants, the flowers, she got annoyed because I would only water anything that was in a direct line between the sun and my shadow, so that I could get a spray bow. So the plants usually were not in that position. But again, you can see some evidence of a supernumerary here.
Yeah.
This is the real rainbow, bottom right.
Yeah. Yeah.
Again, some other examples of this phenomenon.
Yeah.
And this is actually an image from a book, and taken several images actually. Even the original is just beautiful, but because of the number of times that this has been copied, you don't see it terribly well. But this is actually the primary bow. You can see a hint of red there, and there are in the original about 5 or 6 supernumeraries.
Wow.
These are interference fringes,
Wow.
and in fact they're the same kind of thing that you get when you look at a bright light through your hand, which I need to find on the screen, at the little gaps between your fingers. You can see vertical patterns, light and dark. Okay.
Wow, look at that.
Yes, this is a great one, and there's an even better one.
It is so cool.
This is taken from Earth Science Picture of the Day, and I should there's a reference here to it, but this is taken over, I believe, Queensland, and you see a beautiful circular rainbow.
Wow.
Now, the rainbow is not an object; it's an image. We can't walk through it. It's at an infinite distance, but the raindrops producing it, of course, are at a finite distance. So you're looking in a direction. You can't back up with your camera and get more of the rainbow in the picture, in the field of view, unless you're using a fisheye lens, of course. So it's an image, a distorted image of sunlight. So the drops that scatter the light into the eye essentially lie on cones with the vertex at the eye. So here's the cone, and what we're seeing are a distribution of colors in that general direction. Okay, so for an ostensible spherical raindrop, light from the sun comes in at a certain angle of incidence. This is really the only geometric aspect we'll talk about. Is refracted inside the drop and reflected at the far side, and then refracted out again. You can calculate the angle of deviation from the original direction by simple geometry and using basic trigonometry and calculus to determine where the most intense portion of that region of that light will be. It turns out to be, you use the first derivative test to find out that there is in fact a minimum of this deviation angle. Now, of course, the colors, each color is refracted slightly differently because the speed of light, the refractive index of light, is dependent on the wavelength very slightly. So the primary bow has an angular size of about 1.5 degrees from red to violet, which is about 3 times the angular width of a full moon.
Wow.
0.5 degree. But the interesting thing is, with the full moon, you can actually cover it with a baby aspirin, low dose aspirin held at arm's length. So the images of huge moons on the horizon are optical illusions or just outright lies. So again, different drops contribute different colors to the eye. So when you're looking at a rainbow, you're seeing light coming from many different droplets, and each person sees a different rainbow. If you're standing next to me and we're both looking at rainbows, they're different rainbows because it's different cloud droplets or raindrops that are scattering the light into your eyes.
Interesting.
So we get our own personal rainbow. And again, just illustrating these features, the secondary bow is at that half cone angle is at about 52 degrees. And so that's why you see it above the primary. This is a spray bow from a waterfall that in Yosemite National Park. The waterfall was to the left of the picture, and the wind was blowing the spray over.
Wow, this is fascinating.
And you can see the background as well. It's kind of cool. So I call that my spray bow. Again, referring to how thick a rainbow is. My friend Maria Freitas posted this on ePod, it gave me permission to use it. His finger's about 2 degrees in width. So there we have about 1.5 degrees there.
Mm.
What about the pot at the end of the rainbow? Well, I'll just show you my favorite here. And a porta potty. That's some building site. So just, again, interesting juxtaposition.
Mm.
All right. Another question we can ask is, how can cloud droplets produce iridescence? You sometimes see these metallic pastel-like colors on clouds, especially if you're wearing polarizing sunglasses. Just going through a lot of different patterns here. Snowflakes generally possess hexagonal symmetry. And what is interesting is that in all these types, it's a reflection, really, a consequence of the hexagonal structure of ice at the molecular level.
Mm.
And that's manifested at the macro level to a great extent. And talking of ice crystals, in cirrus clouds, there are hexagonal ice crystals. They're composed entirely of ice crystals. And some of them are like flat plates and others are like rods, as seen here. And they can give rise to things called ice crystal halos, cirrus clouds. Why are they circular? Now, this is a rather poor image, but you should never look directly at the sun, of course. Cover it with your hand or a neighbor's cat or a chimney or something like that. And you can't see terribly well, but this is got a reddish tinge on the inside. I've got some other examples. Here's a better one. And there again, you can see the reddish tinge. What's happening is, I'll show you in a minute what the geometry of it. It's a bit like a rainbow, except it's an ice bow, but there's no reflection in those ice crystals. It's pure reflection. These are some others. I've got a little collage here.
Wow.
Remember, smoking is bad for your health, so don't do that. What's going on is that with
this is so
myriads of randomly tumbling ice crystals, essentially they're nearly regular hexagons in cross section. Light from the sun comes in at side 1 and exits at side 3. So you can do a similar calculation to that of the rainbow and find that there's actually a deviation of 22 degrees, minimum deviation, as the light comes through side 1 and exits side 3. That's a minimum. So there's other aspects to it. You get sort of tails to these things. But when they're randomly tumbling, you get these circular arcs. But if they're larger and not randomly tumbling, so if I can show you here, if they're just basically oscillating more or less at the same, falling down at the same rough angle, then everything's concentrated into what are called sundogs, colored splotches on either side of the sun. They're called sundogs because they dog the sun, but they also are known as parhelia, parallel to the sun at the same altitude. So again, this is another example of that, this concentrated light at 22 degrees, but sometimes you'll get a tail because there are other angles at which this light is being deviated. This is just a minimum or an extremum.
This is so cool.
One time I was walking across campus and a student in my mathematics in nature class pointed up at about 85 degrees from the horizon, really up high. Professor Adam, look at that rainbow in the sky.
Right.
And I looked up and I saw this thing, and clearly it's not a rainbow. It wasn't raining. It was a beautiful, crisp November morning. And also it's the wrong way around for a rainbow. So I had a bit of a problem. Do I give her an F because she got it wrong? It wasn't a rainbow and it wasn't raining. Or do I give her an A because she noticed it and I didn't? So I like to say that's why God gave us the grade of D- as a suitable compromise. But anyway, seriously, this is called a circumzenithal arc.
Wow.
And it's one of the purest sets of colors you get from ice crystals. What's going on here is that the light is going in a different direction through these hexagonal crystals. And in fact, it's going through a vertex angle of 90 degrees, which gives more spread, more deviation inside the drop, inside the crystal. This is an example of what's really a complementary display called the circumhorizontal arc.
Wow.
And to go back to this picture here, this will only occur, you will only be able to see this high display if the sun is low enough, below about 32 degrees above the horizon. Whereas here, this circumhorizontal arc is low in the sky, but will only appear if the sun is at an altitude greater than about 58 degrees in the sky. Now, this has been called a fire rainbow, which is nonsense. There's no fire and it's not a rainbow. But you can see it's again caused by the presence of crystals in these clouds, because where there's no cloud, you don't see it. And that's a beautiful display. Parallel, it's at the same level, latitude or altitude as the sun. Here's some pictures going on. Now, here's what's going on. This is a side view of this hexagonal plate crystal. So light is coming from a high sun, refracted through and out. And the observer here, here's your eye, is looking in this direction. And you see a low display. That's the circumhorizontal arc. If the sun is too low, you get something called total internal reflection, and you don't see it. And by reversing the directions, you can see the same cause for the circumzenithal arc. Low sun, high arc. And then there's plenty more.
Wow, look at
that.
that.
Lens, at the South Pole by mathematician Walt Tape. And there's all sorts of things going on here.
This is crazy.
This is the 22-degree halo. This is called an upper tangent arc, which, depending on the altitude of the sun, can look like a bird's wings, and then it merges into something else. This is a portion of a 46-degree halo. This is a parhelic circle caused by reflection from the front side of these crystals, and there's all sorts of other things. I've got this is a complete fisheye view. This here is the circumzenithal arc. This is the 22-degree halo, which is the most common. These are sundogs, and there's all sorts of other things. Really, some of these are very rare halos. But there's many types of halos, and I will often see the 22-degree halo and sundogs walking to work. More commonly do I see them than rainbows in living here in Virginia. There are things called glories.
Wow, look at
that. A set of series of circular concentric rings around the shadow of the observer, if best seen from an airplane or if you're on a high.
This is a cool photo. Really nice.
Yes. Now, this I took actually on the way back from my mother's funeral, which I thought was really kind of neat. And so you can, if you're on the shadow side of the plane, look for the shadow of the plane, or at very least the shadow of the condensation trail, because at the tip of that tail you will see your the glory. They're quite faint, and they're much smaller than rainbows. Here's another example. This is the shadow of the condensation trail, and here are some of the rings. They are actually caused by backscattering of light from cloud droplets, which are much smaller than raindrops. And it's much more mathematically complex than even the rainbow to describe. And what I described was, for the rainbow formation, was basically high school level geometry. It gets much more sophisticated, but at least that high school level geometry and calculus can explain the position and angle associated with the rainbow. In fact, it was said by one of my friends, that Ray Lee, that Descartes could hang the rainbow in the sky, but only Newton could paint it, because Descartes knew the basic geometry of Snell's laws of reflection and refraction, but Newton discovered the splitting of white light into its constituent colors. So I think that's kind of a nice clip. Here's an even better picture of a glory. It's absolutely fascinating.
Yeah, it is. It's so pretty. It's so nice.
It is. It's a beautiful phenomenon. And then there's a thing called corona. Now, again,
wow.
This was taken by me as I was on I was on the wrong side of the plane, really. Sometimes I get my left and right mixed up. But anyway, I was looking through the window which had lots of minute droplets on it, condensation droplets. And so what you have here is a reflection, a distorted reflection of the sun, reflected from the engine housing here and being transmitted back through those droplets, which were diffracting the light into a distorted corona, as it's called. This is not to be confused with the solar corona, something completely different, and also not to be confused with a favorite beer of mine. Mexican beer, nice with lime. Websites you should visit regularly: Optic's Picture of the Day, OPOD, and associated with that is called actually the main site is Optic's Picture of the Day, but you will find different pictures put in over a regular period of time, submitted by people to Dr. Cowley, and he will put them there with interesting explanations. And then Earth Science Picture of the Day, which is a wonderful site and very useful for educational purposes, because it's a project linked with the University Space Research Association, and they have a lot of links for students, for high school kids there. And I've published probably about 50 over the years, pictures there on that, and you can search for that.
For sure.
Now, our department website that I'll give in a minute has a link to two 12-minute videos entitled Nature's Mathematics. In fact, only yesterday I had a nice email from a lady who had been watching it with her daughter, and the daughter was 10 years old, and they loved it. So now the company that produced it is called Curiosity Stream, and they own these, so I can't share them except through the department website.
Right.
They've done wonderful graphics, even if you have to listen to me drone on in the background. And so if you go to the Old Dominion University web page, I should have put that odu.edu. So that part, that's my email address, but the odu.edu would get you to the university web page, and you can find the mathematics department. But they've got the links to those two episodes there, and this is what the screen would look like when you get to that point.
Sure.
They're each about 12 minutes. People have this idea about mathematics, that advanced mathematics is just doing longer sums. And they think, if you're a mathematician, you must be good at accounting or something like that. I mean, it's silly. So the way I try to approach it is, particularly for younger people, everybody loves nature. I don't think there's anybody who's really, hates nature. And as I showed near the end of that talk, the presentation, there was lists of things that you can see in nature that have mathematical aspects to them, different shapes and patterns and so on. And I think for young children, a nature walk and just pointing out these things and encouraging them to look for patterns, along with their natural curiosity and love of nature, into questions about the patterns. Why does this? And that can lead on. You don't have to have all the answers. None of us have all the answers, but it can be a process whereby we say, okay, I'm going to find out more about this. I will. It's very important, of course, for educators to be honest and say, I don't know the answer to that, but I think I can help you find it.
People, thank you for listening. I hope you enjoyed it. Please support us by subscribing to our channel, High Unlock Maths. Till the next episode, be a maths lover.